Hey, we're the Green Outlet team, and the goal of this project is to create a smart outlet that uses Bluetooth wireless communication. And this outlet has three modes: the manual mode, which allows you to turn it on and off, and a sensor mode, which has a user inputted threshold where you can input a threshold and you can turn the outlet on and off based on that threshold. And it has an algorithm mode, which simulates the coordinated charging of electric vehicles.
Alright, so I'm going to talk to you guys a little bit about our algorithm mode. This algorithm is used to coordinate the charging of electric vehicles over the course of the night. I'm just going to jump right into it. So the first step is, does your electric vehicle need charge? So if you've already reached your minimum state of charge, then you don't need charge, you're good to go. But if you do, then what you're going to do is roll the die. What that means is you generate a random number between 0 and 1. Based on what you get for that random number, you're either going to be allowed to ask the grid for a charge packet or not. So let's say hypothetically you roll the die and you are allowed to ask the grid for one charge packet. Then the grid will respond, okay, we do have available capacity for you and you can begin charging. Or it'll say, no, we don't have the available capacity for you to start charging your vehicle, so you can't start charging, and you have to wait a one charge epoch until you can ask the grid for power again. Meanwhile, you're going to be shifting probability states. So these probability states are used to determine how frequently you're allowed to ask the grid for power. So if you ask the grid for power and they do have available capacity, then you will move up a probability state or stay at the highest probability state. If you ask the grid for power and they don't have the available capacity, you will move down a probability state. So over here you can see the probability states. For our project, we have three probability states. There's 0.5, 0.75, and 1.0. So if you ask the grid for power and you're in the highest probability state, that means every time you want to ask the grid for power, you'll be allowed to. But let's say they don't have available capacity for you to start charging, then you'll move down a probability state to the middle state, and then only 75% of the time you'll be allowed to even ask the grid for power. Let's say you get another yes for that roll of the die, but they still don't have any available capacity, then you would move down another probability state, and you would only be able to ask the grid for power 50% of the time. If you do get another yes and they do have available capacity, you would move back up. So what probability state is dependent on the availability of capacity. And the reason that these probability states exist is to limit the amount of communications that go on between electric vehicles and the utilities. If you imagine this scheme being implemented for thousands of vehicles, there would be a lot of communication back and forth between the vehicles and the utilities. So to try and minimize that amount of communication that's going on, you limit the amount of times that people are allowed to request power from the grid. Alright, so here's our green outlet in action. So we're going to come over here, going to go into the control settings, going to pick outlet 2, and we're just going to turn it right on. And there goes our fan, cooling down the room. Now just turn it off. Next we're going to set our other outlet into sensor mode. So you just move your slider along here, and then we'll hit the lights, and it turns on. Turn the lights back on, and it turns off.
So a big part of our project is actually quantizing the electrical power consumed by a plugged-in load, and that's done using a small test resistance in series with the load. If we measure the voltage over the test resistance, we can do some math to figure out the series current through the device and the test resistance. With the series current, if we're also measuring the wall voltage, if we multiply those two values together, we'll get the total electrical power, since the test resistance power is pretty negligible.